Hi, I'm Fisher, and in this talk, I'll be giving a quick intro to our work, Tailors. Today, many important applications represent data using tensors. Much of these tensors consist of zero values, shown in white, and there are very few non-zeros, shown in blue. And this is a property known as sparsity. These tensors are often too large to fit entirely on chip, and so a standard way to solve this is to tile the tensors, dividing them into smaller chunks that can each fit on chip, to improve on-chip data reuse and reduce expensive off-chip data movement. When tiling sparse tensors, it's important to consider that the sparsity is distributed unevenly throughout the tensor, leading to some tiles having more blank space and some having more non-zero data. An intuitive way to tile is to do so with uniform occupancy. This makes sure that every tile is uniformly occupied by the same number of non-zeros. If we take a look at the buffer, this makes sure that the buffer is always fully utilized by non-zero data. But this leaves us in a treacherous situation, as tiling other sparse operands becomes very hard. An alternative is to build tiles with uniform shape, so that each tile operates on a predictable portion of data, and tiling both operands together is easy. However, occupancy between tiles in the tensor can vary significantly, and this leads to low average buffer utilization. Previous tiling approaches assume that every tile must fit in the buffer, and this leads to problems. Instead, we tolerate it when things don't fit by applying the strategy of overbooking, commonly used by airlines and concerts, to tiling. We're going to take a closer look at overbooking in the context of airlines and extend that to tiling. Airlines sell tickets for seats in their plane and aim to maximize the number of paying customers on each plane. So, we show the tickets sold by the airline and the plane itself. Similarly, we take a tile from a tensor and aim to maximize the amount of data in the buffer. Here, the tile is like the ticket sold, and the buffer is like the plane. Airlines run into a problem where people cancel their tickets before the flight departs. So, if they sell only one ticket for every seat, they can end up with many empty seats on the flight. When we tile, we actually run into the same problem. We don't know how much sparsity is in a tile before we load it. So if we allocate buffer capacity for every potential non-zero, we can end up with a lot of empty space in the buffer, which is shown in red. Airlines solve this by selling more tickets than the plane can fit, with the understanding that some people will cancel. We show this in the box above, from the 8 additional tickets being sold. And again, we can do the same thing. We can size our tile so that it is larger than the buffer can fit in the worst case, with the understanding that most tiles will be more sparse than that worst case. And in this particular case, the assumption holds. With the airline, selling more tickets allows for fewer empty seats in the plane, despite the number of cancellations. And with our buffer, allowing for larger tiles enables less empty space in the buffer for the same sparse tensor. This occasionally leads to times when there are more passengers than there are seats, but this was all by design. Here, we show an example where not enough passengers cancel their tickets, and in this case, we end up with a bump passenger, shown in purple, and similarly, if a given tile was not sparse enough, we end up with bump data, also purple. To solve this, we tolerate it when we have this bump data that does not fit, by giving the data an alternative route to the destination. We propose Tailors to handle this bump data, and Swiftiles to decide how much to overbook by. By combining Tailors and Swiftiles, we achieve a geomean 2.3 times speedup when integrated into an existing sparse tensor algebra accelerator. For more details, please see our paper.